All right, BC Calc, this is going to be your day 60 notes. Day 60, we're finishing up our volume techniques today. We have one more technique to talk about, and that is finding volume by what's called the cylindrical shell. So the nice thing about cylindrical shells is it's a new approach, but it's a different way of thinking about finding volumes in ways that we've already found them. So for example, a cylindrical shell volume could also be sometimes accomplished through disc and washer techniques. So it's just kind of a different thought process behind it and a different approach that you might like better, or you might like going back to disc and washer, and that's okay too. It certainly has its advantages, and you'll see that in today's lesson. So as a review, when we talk about our disc method, it would be something of the following forms: that if we have this plane surface that is attached to the axis of revolution, as I spin it around, we would take the integral from a to b of pi r squared. Okay, pull the pi out. The radius is going to be the height of the function along the interval from a to b. And then if we have something that's being spun around the y-axis, we have to have it of the form x equals f of y. So now we're integrating along those y-axis bounds from c to d for the function f of y squared dy. So that's what we have as a good review of disc. And the nice thing that I like about this is I know my version's in color. It would be so nice if I could get your version to be in color as well, but hopefully the colors are really helping to make some sense as to the three-dimensional nature of taking these regions and spinning them around our axes here. So then we move on to washer, and the whole idea with washer is we get this open area in the middle section, and that to find our volume by washer, we have to take the kind of the larger radius and then subtract the smaller radius squared from that. So you can see in this case, if I take the radius up to the function f of x, subtract out the radius to the function g of x, if we think about those areas and the area that's left over, pi times the integral from a to b of the upper function f of x squared minus g of x squared with respect to x. And then similarly, we can do the same thing with respect to y if we're spinning it around the y-axis. Okay. So those are our two techniques that we know up until this point, and now we move on to our new technique, which is the cylindrical shell method. All right. So you can see in your notes what the cylindrical shell method looks like, but how do we find the volume of a shell? Well, what we have to do is we have to take the area around the outside of the shell, and then we have to multiply by the thickness. So that's going to give us our volume. If we think about the area of around the outside of a cylinder, it's the concept of surface area. So we're doing, let's see, the area around the outside of a circle is going to be, that's perimeter, right? So 2 pi r, and then times the height of the cylinder, that's going to give you the total surface area. So here's what I have for volume. Volume is going to be 2 pi r times the height times the thickness. So this right here is kind of covering the outside of the cylinder, the 2 pi r h. That's your concept of surface area. If you then multiply by the thickness of the cylindrical shell that we're using, that's going to give you volume. And as you add up the volume of all those cylindrical shells, that gives you the total volume that we're looking for along our interval that we're spinning around an axis. So we'll see how we can use the cylindrical shell technique in an example in just a moment. But I think the next page also has some good diagrams to kind of refer to in terms of taking this plane surface here. If you want to spin it around a vertical axis of revolution, the thing that's unique to cylindrical shells is when you draw that rectangle in and you spin it around the vertical axis, notice how the rectangle that's drawn in is parallel to the axis of revolution. Whereas our other two techniques of disc and washer, when you draw the rectangle in, it's perpendicular to the axis of revolution. Okay, so if I were to spin this around the horizontal x-axis, this would be a disc right here. And the rectangle will be drawn perpendicular to that axis. But as I spin this around the y-axis, you can see that this is the resulting figure right here. Notice how that rectangle is parallel to the axis of revolution. So this is still integrating with respect to x, right? You would find the area of that region with respect to x, and then multiply by the thickness to get that cylindrical shell idea. But it's going to be sort of combining two ideas where you can now rotate this around a vertical axis, but we're integrating the area underneath with respect to x, which is a little different than what we would do if we were doing washer or disc. So here's a practice example. Find the volume formed by rotating the region bound by 3x plus 2y equals 6, x equals 0, and y equals 0 around the y-axis. All right, so here we go. Let's draw a picture of what we got going on here. All right, we know x equals 0 and y equals 0 are our axes, right? So we got x equals 0, or sorry, y equals 0, x equals 0. And then 3x plus 2y equals 6. When I graph this, that's going to be 2y equals negative 3x plus 6. So y equals negative 3 halves x plus 3. All right, negative 3 halves x plus 3. That's a line that has a positive y-intercept. And the slope of negative 3 halves would make the x-intercept of the line at positive 2. So we're going to get this region right here. Right, here's the line. We're going to take this area right here. We're going to spin it around the y-axis, or rotating around this way. And when I rotate around that way, we're going to get this sort of cone-like shape, right? But the idea is, although we have other techniques and ways we can find this volume that we've learned prior to shells, I want to see if we can approach this from a shell technique, all right? So what we're integrating is we're doing 2 pi RH, which is the surface area of the cylinder, times the thickness. And the thickness is going to be delta x, which is our dx. Okay. Now, because the constant here is 2 pi, we can pull out that 2 pi. So we need to figure out what is the radius and what is the height in terms of x here. So the bounds of integration, by the way, for the area of this region that we're spinning around are from 0 to 2. So that's why it was kind of important to know where we hit the x-axis here. So we know we're integrating from 0 to 2, but we need to know what is r and what is h with respect to x. Well, let's actually draw in the shell and see what we're looking at here. If I take this rectangle right here, okay, and I were to spin it around the y-axis, we're going to get this rectangle to kind of match up with it over here. And the shell that we're looking at, it's a little tough to sketch, but we get this cylinder that looks like this. Okay. So think about taking this cylindrical shell right here. We're taking this rectangle, we're revolving it around the y-axis. You're going to get this cylinder right here. Okay. So in order to determine the radius and the height, the nice thing about the radius is that when you're doing cylindrical shells, the radius is typically either just x or y. And in this case, no matter where you draw the radius at any given value is just going to be a length of x. Whereas the height of the cylinder is dependent on the function here. The height at any given rectangle that I draw is going to be the height to the curve negative 3 halves x plus 3. So no matter where I draw my shell, the radius is a length of x in general. Doesn't matter where I draw it. And then the height of the cylinder is going to be the height at that curve, negative 3 halves x plus 3. And as soon as I know that, we can sub in that the radius is x, the height is negative 3 halves x plus 3. And now we can integrate with respect to x. So distributing that x in real quick to make my job a little bit easier, we'll get negative 3 halves x squared plus 3x. And now if we use our anti-power rule, up this by 1, so that's x cubed, and then we're multiplying the outside by 1/3, so that's going to become negative 1/2 x cubed. Up this by 1, so now it's x squared, so plus 3 halves x squared. Okay, we're integrating from 0 to 2, and we got to multiply by 2 pi. Okay, and these will always have 2 pi, because remember, you're finding the surface area around the outside, which is 2 pi r, circumference times the height, is going to be the surface area, times the thickness, which is your dx. Okay, so if I plug in 2, we're going to get 2 pi times, let's see, 2 cubed is 8, and negative 1/2 times 8 is negative 4, plus 2 squared, 4, 2 goes into 4 twice, times the 3 is 6. And when I plug in 0, you'll just be subtracting 0 there, so 2 pi times 2 is 4 pi units cubed. That is the resulting volume from taking all of these shells and spinning them around the y-axis. Okay, that would be the volume of that solid of revolution there. Okay. But here's the thing. When we drew this initially, if you're looking at that, you might have thought, well, why don't we just use disk method to do this? And the thing is, you certainly could use disk method. But the nice thing about using shell is that when I use shell, because we're drawing rectangles parallel to the axis of revolution, we can integrate pretty easily with respect to x. We have to shift our mindset a little bit when we're thinking about using a disk, because now I have to draw my rectangles perpendicular to the axis of revolution, spin them around, and that's going to be now with respect to y. So let's try it though. Let's use the disk method, confirm that we get the same exact results. So in the disk method, if we just kind of resketch our image real quick, here was the line. This is the region that we're rotating around, so it's going to look something like this. Okay. All right, here are the disks that we're looking at. Okay. So when I use the disk method, if we're rotating around the y-axis, we need to be integrating with respect to y. So take your linear equation, 3x plus 2y equals 6, and get x in terms of y now. So x would be, if I subtract the 2y over, divide the 3, negative 2/3 y, and then plus 2. Okay. So just keep in mind, we also have to change the bounds of integration when we integrate with respect to y. So it's going to be from 0 to 3, where that y-intercept is. So we're integrating from 0 to 3 of, at any given moment, the radius is negative 2/3 y plus 2. So we're going to take that radius and square it times dy for the thickness there. Okay. All right, once you have that integral set up now, actually, you know what, before, let me change that into an integral. Let's actually expand that real quick so that this way we can figure out what we're integrating. It's going to be 4/9 y squared. And then if you have two of those negative 2/3 y terms, so it's going to be negative 4/3 y twice for negative 8/3 y in the middle with a plus 4. Okay, now that I have that expanded, now we can find the antiderivative, which would be pi. If I up this, that's now y cubed, divide by a third out front, so that's 4/27 y cubed. Up this by 1, so that's squared, multiply by a half, so that's minus 4/3. When you simplify, y squared plus 4y. Okay, and we're integrating from 0 to 3. All right, let's plug in 3. We know the lower bound of 0 is just going to subtract at 0 in the end. I hope this is going to get me to 4 pi. That's what the answer was when we used shells a moment ago. If I plug in 3 for y, that's going to be 27. So that's nice that it cancels with the 27 down there to leave you with the 4. Plug in 3 here. 3 squared is 9. 3 goes in 3 times. So that's going to be a minus 12 there. Oh, and then a plus 12 at the end. How nice is that? 12s cancel. And you get that the volume using disks is the same, 4 pi cubic units. So you now have those two methods to kind of compare and contrast here. If you like the way disk looked, that's fine, but keep in mind that when I took this rectangle right here and I spun it around the y-axis, we're now integrating with respect to y. So we have to get x in terms of y, which was not a big deal, and make sure that we're using the appropriate bounds. It will take us a little bit longer, I think, to now get used to this shell method, but shell method certainly has its advantages as well. Okay, the radius is either going to be x or y typically, and then the height along the function. The height of each shell was the height to the function negative 3/2 x plus 3. All right. We're going to do one more shell method for practice, and it happens to be an example that we looked at yesterday that was a washer example. So the washer that we took a look at yesterday was the area bound by these 3 lines, and we spun it around the x-axis. And we saw the resulting region when you do the cross sections were a bunch of washers. But that's if I was drawing the rectangles perpendicular to the axis of revolution. Let's see what happens when we make them such that they're parallel. So here we go. X equals 1 right here. Y equals 1. And the line y equals x plus 1 is this line right here. So as I'm sketching this, maybe this is starting to look familiar, that this was the region right here, okay, that we were spinning around the x-axis. And when I spin that around the x-axis, we're going to get this very similar looking triangular region down here. Okay. I remember yesterday we drew some washers in there such that when I draw in that vertical rectangle, we would take the big radius from the x-axis squared minus the small radius squared and integrate with respect to x and those bounds right there. Well, the difference now is that when we use the shell technique, we're going to draw a rectangle such that it's parallel to my axis of revolution, which is the x-axis. So when I draw on that shell here, let me draw kind of the matching rectangle over here. Okay. We need to determine what the radius and the height of the shell are. Okay. So here's my shell that we're looking at. Okay. So right underneath this, I'm going to write radius, and I'm going to write the height. Okay. So what's the radius? The radius, like I mentioned in the other shell that we did, at any given moment, if I were to draw a shell, the radius is just the value of y. Okay. It's just going to be the height above the x-axis. So the radius in general is y. Now, the height that we're talking about right here is this height, right? You have to kind of think of it this way. So the radius is just y along the y-axis. But the height that we have is going to be the difference in 1 minus y minus 1, because we have to get in this linear equation, since we have something that's being drawn to the y-axis. We're going to be integrating with respect to y here. So if you get x alone, x equals y minus 1. So if we're looking at the height here, from here to here, we know is 1. So if this to the line is y minus 1, we're going to take 1 minus y minus 1. And if I distribute the negative there, we get 2 minus y. So the height at any given moment of the cylindrical shell is going to be represented by 2 minus y. And if I use my shell formula, remember it's 2 pi on the outside whenever you're using a shell, because 2 pi RH is the surface area that we're taking. So it's 2 pi from, my bounds have to go from, all my shells are going to exist from 1 to a height of 2. Those are the bounds of integration here, right? If you look at all those heights, we're taking heights from 1 to 2. Of the radius y times the height of 2 minus y. And we're integrating with respect to y here. Okay. Once you have the setup, and I think the hardest thing is going to be the setup, right? Just visualizing, drawing a picture, making sure you have the correct bounds. From here, the actual integral should be pretty easy to evaluate. So it's going to be 2 pi from 1 to 2 of 2y minus y squared dy. So using anti-power rule, antiderivative would be y squared minus y cubed over 3 with my bounds from 1 to 2, which would be 2 pi times, plug in the 2, 2 squared is 4, and then minus 2 cubed over 3 would be 8/3. Okay, let me get a bracket here. Minus when I plug in the 1, we're used to having a 0 there, so just make sure you carefully plug in the 1. You're going to get 1 minus 1/3. So 12/3 minus 8/3, that's 4/3 minus 1 minus 1/3 is 2/3. So 2 pi times 2/3 that's left over is 4 pi over 3, and this would be cubic units there. If you look back at our day 59 notes in the example that we took our vertical rectangles, spun them around, and got a washer instead, you'll see that we did confirm, and we should be able to see that we got the same exact volume. So next time we're in class, we're definitely going to do more practice sketching using both techniques. We'll see what it looks like when we draw our rectangles parallel to the axis versus perpendicular. And in the end, you should still get the same answer, which is good news. It's all kind of about how you visualize it and what you're most comfortable with using. I would challenge yourself to use some shells, though, because I know that that's going to take a little while to get used to in terms of defining the radius and the height. But once you get used to it, you may find up liking that you or realizing that you like shells. So this practice page, we'll do this next time we're together in class. So we're going to rotate a region around the line y = 6, which we've done a little bit of so far. But if you want, I would say even just see if you can get a picture going for these questions. If you want to challenge yourself and actually try the area volumes, then go for it, right? So try number 1. Number 2 is using cylindrical shells. So if that's still a technique that you're like, I'm not really sure, how we're getting the radius and the height there, we'll talk about this next time we're in class. But if you want to at least maybe get a picture going where you set up and draw those graphs, sketch the area, think about what the volume would look like when you rotate, then that's at least a good setup to get going next time we're together. All right, that's it for volume of cylindrical shells for today. We'll go over some more practice next time I see you. Have a good one. Have a good one.